Picture this. It's January 1943, somewhere in the dark waters off Guadalcanal. American and Allied ships are under constant attack from Japanese aircraft, and conventional anti-aircraft fire is almost useless. Gunners would fire thousands of rounds, hoping to get lucky, praying that one shell might actually hit a fast-moving bomber diving toward their ship. The odds were astronomical, but on that morning, everything changed. A single cruiser, the USS Helena, fired just 3 salvos at a retreating Japanese dive bomber, and something unprecedented happened. The aircraft exploded midair without a single direct hit. The shells had detonated near the plane, shredding it with shrapnel from yards away. The secret, a revolutionary magnetic proximity fuse that would reshape the entire war. But here's where the story gets fascinating. This wasn't just about American innovation. This was about a deadly technological race involving British engineers. Captured enemy technology, and a weakness so fundamental that it nearly cost the Allies everything. Today, we're diving deep into one of World War II's most closely guarded secrets. A weapon so powerful that Winston Churchill ranked it alongside radar and the atomic bomb. We're talking about magnetic fuses, reverse engineering, desperate gambles, and the brilliant engineers who had to crack the code before the enemy did the same to them. By the end of this video, you'll understand why a device smaller than your fist changed naval warfare forever, and why the critical weakness hidden inside almost turned the tide of the Pacific War. Let's get into it. To understand the magnitude of what British engineers accomplished, we need to go back to the beginning of World War II, to a crisis that threatened Britain's very survival. In November 1939, just months after war broke out, German aircraft began dropping strange new weapons into British waters. Ships were exploding and sinking with no visible cause. There were no torpedoes, no contact with visible mines, nothing. Captains reported massive underwater explosions that broke their ships' keels in half, sending vessels to the bottom in minutes. The Royal Navy was baffled. Traditional minesweepers found nothing. Divers saw nothing. It was as if the sea itself had become hostile. The death toll mounted rapidly. Within weeks, dozens of merchant ships had been lost, and the vital supply lines that kept Britain fed and armed were under siege. The Admiralty knew they were dealing with something revolutionary, but they had no idea what it was or how to fight it. Intelligence reports suggested the Germans had developed some kind of magnetic mine, but without a sample to study, British scientists were working blind. Then, on November 22, 1939, fate intervened in the most unexpected way. A German Heinkel bomber, flying low over the Thames estuary during low tide, dropped one of these mysterious weapons. But instead of falling into deep water where it would be lost forever, the mine landed on the mudflats near Shoeburyness at low tide, completely intact and accessible. This was the breakthrough Britain desperately needed, but it came with enormous risk. The mine could detonate at any moment. Nobody knew how sensitive it was or what would trigger it. A team of bomb disposal experts from HMS Vernon, Britain's premier mine warfare establishment, was immediately dispatched to the site. These men, led by Lieutenant Commander John Ouvry, approached the cylindrical device with extreme caution. They knew that magnetic mines could be triggered by the Earth's magnetic field interacting with large metal objects, so they stripped themselves of all metal. Every button, every belt buckle, every tool had to be non-magnetic brass or wood. Imagine the tension as these engineers, working in freezing mud, carefully examined this unknown weapon that could explode and kill them at any second. The disarming process took hours of painstaking work. Using specially made brass tools, they carefully opened the mine's casing to reveal its interior mechanisms. What they found inside was both brilliant and terrifying. The Germans had created a sophisticated magnetic sensing unit that could detect the change in the Earth's magnetic field, caused by a ship's steel hull passing overhead. Steel ships naturally concentrate magnetic field lines through their hulls due to magnetic permeability. As a vessel sailed over the mine, this concentration would trigger a sensitive mechanism, detonating hundreds of pounds of explosives directly beneath the keel. The resulting underwater blast would create a bubble of gas that would rise up and literally snap the ship in half. It was devastatingly effective. The mine was rushed back to HMS Vernon's laboratories, where Britain's top scientists and engineers began an intensive reverse engineering effort. They needed to understand every component, every principle of operation, and most critically, they needed to find a countermeasure before German mines strangled Britain's maritime lifeline completely. The team worked around the clock, taking the device apart piece by piece, photographing every component, testing every circuit. What they discovered was that the Germans had created an ingenious system using a dip needle, essentially a sensitive magnetic compass that could detect vertical changes in magnetic field strength. When a ship passed overhead, the needle would tip, completing an electrical circuit and firing the detonator. Understanding the mechanism was only the first step. The British needed to develop a defense, and they needed it fast. Ships were still being sunk daily, and the German Luftwaffe was dropping these mines by the hundreds into British ports and shipping lanes. The solution that emerged from this frantic research would become known as degaussing, a term coined by British scientist Charles Goodhue. The principle was elegant in its simplicity, but challenging in execution. If they could reverse the magnetic field of a ship's hull, they could make vessels effectively invisible to magnetic mines. The implementation involved wrapping ships in electrical cables and passing current through them in a specific pattern, temporarily reversing their magnetic signature. But degaussing was just one part of a larger technological battle that was about to unfold. The British discovery of the German magnetic mine's secrets set off a chain reaction of innovation and counter-innovation that would eventually involve not just Britain and Germany, but America, Japan, and every major naval power. The race was on to develop both more sophisticated magnetic weapons and more effective countermeasures. And at the center of this race was a fundamental question that engineers on all sides were asking: could magnetic principles be used not just in mines, but in something even more game-changing? The answer to that question would come from an unexpected direction and would lead to the development of the proximity fuse, a weapon that would make the magnetic mine look primitive by comparison. While British engineers were mastering magnetic mine technology across the Atlantic, American scientists were pursuing an even more ambitious goal. The problem they faced was different but related. Anti-aircraft gunfire in the early years of World War II was embarrassingly ineffective. Studies showed that it took an average of 2,500 shells to bring down a single enemy aircraft. Pilots joked that the safest place during an air raid was inside the flakburst pattern because the odds of actually getting hit were so low. Traditional shells used either contact fuses, which only worked if you scored a direct hit, or timed fuses, where gunners had to estimate the target's altitude, speed, and direction, then set the shell to explode at a predetermined time. In the chaos of combat, this was nearly impossible. The United States Navy had been quietly working on a revolutionary solution since 1940. Building on British research into proximity detection, at Johns Hopkins University's Applied Physics Laboratory, a team called Section T, led by physicist Merle Tuve, was developing what they called the VT fuse, with VT standing for variable time. This was deliberate misdirection. In reality, they were creating a miniature radar system that could fit inside an artillery shell and would automatically detonate when it detected a target nearby. The technical challenges were staggering. They needed to create a radio transmitter and receiver small enough to fit in a 5-inch shell, rugged enough to withstand the shock of being fired from a gun, which generated forces of 20,000 Gs, and reliable enough to work every single time in combat conditions. The heart of the VT fuse was a set of miniature vacuum tubes, the same technology used in radios of the era but scaled down to an almost impossibly small size. These tubes had to survive being spun at 25,000 revolutions per minute as the shell spiraled through the gun's rifling, and they had to function perfectly while the shell traveled at 2,800 feet per second. The engineering required was extraordinary. Scientists developed special rugged vacuum tubes with reinforced elements. They created circuits that used the shell's own body as an antenna. They designed safety mechanisms that kept the fuse from arming until it was a safe distance from the firing ship. Every component had to be tested, refined, and tested again. By August 1942, after 2 years of intensive development, the VT fuse was ready for its first real-world test. The cruiser USS Cleveland, equipped with proximity-fused 5-inch anti-aircraft shells, faced off against remote-controlled drone aircraft in Chesapeake Bay. The results shocked everyone present. The Cleveland destroyed 2 drones in rapid succession with such efficiency that the Navy officers running the test literally ran out of drones. They found one more the next day and sent it up. The Cleveland annihilated it almost immediately. The proximity fuse worked, and it worked beyond anyone's most optimistic predictions. The shells would broadcast radio waves that bounced off the target aircraft, and when the return signal indicated the target was within lethal range, the fuse would trigger, creating a devastating airburst that showered the aircraft with high-velocity shrapnel. But here's where the story connects back to magnetic technology and British reverse engineering expertise. The VT fuse represented such a significant technological leap that the US military treated it as one of the war's most closely guarded secrets, on par with the Manhattan Project. There was a very real fear that if the enemy captured an intact fuse, they could reverse engineer it and develop their own version, or worse, find a way to jam the radio signals and render the weapon useless. The British had proven with the German magnetic mine that reverse engineering was not just possible but could be accomplished quickly by skilled engineers. Therefore, the US Navy imposed strict rules on VT fuse deployment. Initially, they could only be used over water, where a dud shell would sink to the ocean floor and be The combat debut of the proximity fuse came on January 5, 1943, in exactly the kind of scenario that its developers had envisioned. A task force, including the cruiser USS Helena, was operating near Guadalcanal when Japanese dive bombers attacked. Lieutenant Red Cochran, commanding the Helena's aft 5-inch battery, opened fire on the retreating aircraft with VT-fused shells. His second salvo brought down a Val dive bomber that was already pulling away from the attack. The shells exploded near the aircraft without direct contact, and the shrapnel tore it apart. This was the first combat kill attributed to a proximity fuse, and it validated everything the engineers had promised. Word spread quickly through the Pacific Fleet. Here was a weapon that turned near misses into kills, that made the target effectively 50 times larger than it actually was. Throughout 1943 and into 1944, proximity-fused ammunition transformed naval anti-aircraft warfare in the Pacific. Whereas before, Japanese aircraft had enjoyed relatively free rein to attack Allied ships. Now the sky around American task forces became a deadly gauntlet. Studies showed that while conventional timed fuses required an average of 1,000 shells to down one aircraft, proximity fuses needed only about 250 rounds per kill, a fourfold improvement in efficiency. More importantly, the psychological impact on Japanese pilots was significant. They watched their fellow airmen being blown out of the sky by shells that seemed to have a mind of their own, exploding with uncanny precision even when they appeared to miss by yards. This defensive capability became even more critical as the Japanese, facing mounting losses and increasing desperation, began developing their kamikaze tactics. The proximity fuse would prove essential in defending against these suicide attacks, where even a damaged aircraft could still reach its target. As American proximity fuses were revolutionizing Pacific naval warfare, British engineers faced their own challenges with magnetic and proximity weapons. The knowledge they'd gained from reverse engineering German magnetic mines had given them insights that American scientists were eager to tap into. In 1940, a British technical mission called the Tizard Mission had traveled to the United States, bringing with them a treasure trove of military secrets, including early research on proximity fuses, cavity magnetron technology for radar, and detailed intelligence on German magnetic mines. This exchange of information created a unique partnership where British theoretical knowledge combined with American industrial capacity to produce weapons that neither nation could have developed alone. But the magnetic mine crisis in European waters continued to evolve in unexpected ways. Even as degaussing protected Allied ships from the original German magnetic mines, the Germans introduced increasingly sophisticated versions with combination triggers. Some mines would count the number of ships passing overhead before detonating, making minesweeping operations treacherous because sweeping ships might not trigger the mine even if they were close enough. Others combined magnetic, acoustic, and even pressure sensors, requiring multiple stimuli before they would detonate. The technological cat-and-mouse game between mine developers and mine countermeasure specialists became extraordinarily complex. British engineers at HMS Vernon found themselves constantly analyzing new mine variants, each requiring new sweeping techniques and new defensive measures. One of the most ingenious British responses to the magnetic mine threat came in the form of the Wellington DWI aircraft. DWI officially stood for Directional Wireless Installation, another piece of deliberate misdirection, but aircrew called them flying donuts for obvious reasons. These specially modified Wellington bombers carried enormous electromagnetic coils, 48 feet in diameter, powered by Ford V8 automobile engines. The coil generated a powerful magnetic field that could trigger German magnetic mines from a safe altitude above the water, flying low and slow over suspected minefields. These aircraft would literally fly a pattern that caused mines below to detonate harmlessly in their wake. It was dangerous work. The aircraft were unarmed, slow, and vulnerable, and they had to fly predictable patterns at low altitude in areas where enemy aircraft might appear at any moment. Yet the Wellington DWI crews persisted, clearing vital shipping lanes and harbors throughout the war. The global nature of the magnetic weapons race meant that intelligence about enemy developments was crucial. British code breakers at Bletchley Park, already famous for cracking German Enigma codes, also provided valuable intelligence about German mine-laying operations. This information allowed British minesweeping forces to concentrate their efforts where they would be most effective. Meanwhile, American signals intelligence in the Pacific was tracking Japanese mining efforts, though the Japanese never developed magnetic mine technology to the same degree as the Germans. Japan's mining efforts focused more on traditional contact mines and on defending their home waters in captured territories with extensive minefields. However, the Japanese did make significant efforts to develop their own proximity fuse technology late in the war, though they approached it from a different angle than the Americans. Japanese engineers developed what they called a photoelectric proximity fuse for aerial bombs. This system used light-sensitive cells that would trigger when the shadow of a target passed beneath the falling bomb. It was ingenious in its simplicity and didn't require complex radio components. But it had critical limitations. It only worked in daytime and could malfunction if the sun's angle was wrong. The Japanese tested these devices, but deployed them only once operationally. In the war's final weeks, far too late to affect the outcome. Had they developed this technology earlier, or if they had captured and successfully reverse-engineered an American VT fuse, the Pacific War might have taken a very different turn. This brings us to the central tension that drove security measures around proximity fuse technology. Every nation involved in the war understood that magnetic and proximity sensing represented the future of weapons technology. The nation that mastered these principles first would have an enormous advantage, but the nation that lost control of the technology to an enemy who could reverse engineer it would face disaster. British intelligence was well aware that German scientists were working on their own proximity fuse programs. Reports indicated that Germany had over 30 different proximity fuse development projects underway, using various triggering mechanisms including acoustic detection, magnetic detection, photoelectric cells, and even electrostatic field sensing. None of these programs achieved operational success during the war, but the British couldn't know that at the time. The threat of a German proximity fuse breakthrough kept Allied scientists and intelligence agencies on constant alert. The security measures around American VT fuses were extraordinary. Manufacturing was distributed across 87 different contractors using 110 factories. Component manufacturers often didn't know what their parts were being used for. The fuses themselves were shipped in sealed containers with armed guards. Ships' captains received strict orders not to use VT ammunition over land where duds might be recovered by the enemy. This restriction frustrated army commanders in Europe, who could see the devastating potential of proximity-fused artillery for ground warfare but were forbidden from using it. The policy held until December 1944, during the Battle of the Bulge, when the German offensive was so dangerous that the combined chiefs of staff authorized proximity fuse use over land. General George Patton would later write that the funny fuse won the Battle of the Bulge, crediting it with killing over 700 German soldiers in a single artillery barrage. The proximity fuse's effectiveness against V-1 flying bombs over Britain further demonstrated its value and its vulnerability. When the Germans launched their V-1 campaign against London in June 1944, British anti-aircraft defenses were initially ineffective against the small, fast cruise missiles. But when American proximity-fused shells were deployed, the kill rate soared to 79%. This was a spectacular success, but it also meant that hundreds of VT-fused shells fell on British soil, some as duds. British and American intelligence services worked frantically to recover every single dud before German agents could find one. Special teams with metal detectors swept areas where VT shells had been fired, racing against time in German espionage efforts to secure the technology. Now we come to the critical weakness that made all of this revolutionary technology vulnerable, a flaw so fundamental that it threatened to unravel everything the Allies had achieved. The weakness wasn't in the design of the proximity fuse itself, or in the magnetic mine detection systems. It was in the very principle that made them work. Magnetic field detection and radio wave propagation, both technologies were susceptible to countermeasures, and if the enemy understood the principles well enough, they could potentially neutralize the weapons entirely, or worse, turn them against their creators. This vulnerability kept Allied scientists awake at night and drove the obsessive secrecy around these weapons programs. The magnetic principle that made mines and certain proximity detection systems work was actually quite straightforward, which meant it was also potentially easy to counter once you understood it. A steel ship's hull concentrates Earth's magnetic field lines, creating a detectable magnetic signature. But this signature could be manipulated or eliminated through gassing. British engineers had proven this when they defeated German magnetic mines. The fear was that if Germany or Japan captured and studied an Allied proximity fuse that used magnetic principles for target detection, they would immediately understand how to counter it. More importantly, they might develop their own versions and deploy them against Allied aircraft, turning strategic bombing campaigns into suicide missions. The B-17 and B-24 bombers that were pounding German industry into rubble would become sitting ducks if German anti-aircraft guns gained proximity fuse technology. The radio-based VT fuse had its own vulnerabilities. Because it worked by broadcasting radio waves and detecting their reflection off the target, it was theoretically susceptible to radio jamming or spoofing. A clever enemy could potentially broadcast signals on the same frequency, causing premature detonation or preventing detonation entirely. The Americans had designed the fuse to operate on a specific frequency range and had incorporated some basic anti-jamming features. But these were limited by the size constraints and the technology available in the early 1940s. More sophisticated electronic countermeasures could potentially render the weapon ineffective. This is why captured German documents showing their research into radio countermeasures were taken so seriously by Allied intelligence. Any hint that the Germans understood the radio principles behind proximity fuses triggered immediate security reviews. There was also a more subtle vulnerability that British engineers identified through their experience with magnetic mines and countermeasures. Every technological advantage in warfare eventually gets countered, and the side that recognizes this earliest has a crucial edge. The British knew from their own reverse engineering success with German magnetic mines that no technology remained secret forever. Therefore, they pushed for constant innovation, always working on the next generation of weapons, even before the current generation had proven itself in combat. This philosophy led to research into combination fuses that used multiple detection methods, making them much harder to counter. A fuse that used both magnetic and radio detection, or that combined proximity sensing with impact backup triggers, would be far more robust against enemy countermeasures. The most serious vulnerability came from the production and deployment side, with tens of millions of proximity fuse shells being manufactured and shipped to combat zones worldwide. The probability of one falling into enemy hands increased daily. Every shell fired over land was a potential intelligence leak. Every dud that failed to detonate was a gift to enemy engineers. The U.S. Navy's decision to restrict VT fuse use to over water was wise, but it couldn't eliminate the risk entirely. Shallow water, beaches, islands, all of these presented opportunities for enemy recovery operations. British and American intelligence services tracked German and Japanese salvage operations, trying to determine whether any proximity fuses had been recovered. Photo reconnaissance missions looked for signs of enemy scientists examining suspicious objects. Signals intelligence listened for any indication that enemy engineers were discussing radio fuse technology. In fact, there is evidence that the Japanese did recover at least one intact proximity fuse late in the war. American shells fired during naval engagements near Japanese-held islands occasionally landed in shallow water or on beaches. Japanese engineers were certainly capable of recognizing the significance of what they found if they examined these shells carefully. However, by the time Japan had any opportunity to reverse engineer VT fuse technology, they lacked the industrial capacity and resources to do anything with it. Their electronics industry was being systematically destroyed by American bombing, and they simply didn't have time to develop countermeasures or their own versions before the war ended. But the Americans couldn't have known this at the time. Every intelligence report suggesting possible Japanese examination of proximity fuse technology triggered alarm bells. The Germans came closer to developing effective countermeasures, though they never quite succeeded. German scientists understood radio principles extremely well, and if they had captured an intact VT fuse early in the war, they might have developed jamming systems or even their own proximity fuses. Some historians argue that if Germany had possessed proximity fuse technology for their anti-aircraft defenses in 1943 and 1944, the combined bomber offensive that devastated German industry might have failed, potentially extending the war in Europe by months or even years. The sheer number of Allied bomber crews that would have been lost to proximity-fused German flak is almost impossible to calculate, but it would certainly have been catastrophic. This is why the security around VT fuses was so intense, and why officers who violated the over-water-only restriction faced court-martial. The philosophical question that British engineers and American scientists grappled with was this: how do you deploy a weapon that's so effective it could change the war's outcome, while simultaneously preventing the enemy from learning its secrets? The answer involved layers of security, from compartmentalized manufacturing to strict use restrictions, from rapid dud recovery operations to sophisticated intelligence gathering about enemy countermeasure programs. But ultimately, there was no perfect solution. Every proximity fuse fired was a calculated risk, a bet that its military value in that moment outweighed the potential cost if the enemy recovered it. That this calculated risk paid off is evident in the outcome of the war, but it was never a certainty. British experience with reverse engineering had taught them another crucial lesson. Innovation breeds counter-innovation, which breeds counter-innovation. In an endless technological spiral, the magnetic mine led to degaussing, which led to acoustic mines, which led to new sweeping techniques, which led to combination mines with multiple triggers, and so on. This cycle meant that victory didn't go to whoever developed the best single weapon, but to whoever could maintain a sustained pace of innovation, always staying one step ahead. The proximity fuse represented a massive leap forward, but British and American engineers were already working on improvements and alternatives, even as the first VT shells were proving themselves in combat. The final act of this technological drama played out in the closing years of World War II and revealed both the power and the limitations of reverse-engineered weapons technology. As American forces pushed closer to Japan in 1944 and 1945, the proximity fuse became not just important but absolutely essential. Japanese kamikaze attacks represented a new and terrifying threat where even damaged aircraft could achieve their mission by crashing into ships. Conventional anti-aircraft fire, even when it hit attacking aircraft, often couldn't destroy them quickly enough to prevent them from reaching their targets. The proximity fuse changed this equation dramatically. A kamikaze pilot flying through a barrage of proximity fuse shells faced not just the possibility of a direct hit but a continuous zone of lethal airbursts that could shred his aircraft long before it reached bombing or crashing range. The statistics tell the story clearly. During the Okinawa campaign in 1945, proximity-fused ammunition accounted for a massive percentage of Japanese aircraft shot down by ships' anti-aircraft fire. Navy studies estimated that without VT fuses, the casualty rate among American ships would have been 3 to 10 times higher. When you consider how devastating the actual kamikaze campaign was, even with proximity fuses in use, imagine how much worse it would have been without them. Dozens of additional ships sunk, thousands more sailors killed. The proximity fuse didn't make ships invulnerable to air attack, but it made them survivable in situations where they would otherwise have been overwhelmed. This was the weapon proving its worth at exactly the moment when it was needed most. But even as American forces were benefiting from proximity fuse technology in the Pacific, British engineers were dealing with a different technological challenge in Europe. The German V-1 flying bomb campaign against London had initially seemed unstoppable. The small, fast cruise missiles were difficult targets for both aircraft and anti-aircraft guns. But proximity-fused shells, combined with radar-predicted gunfire control, turned British anti-aircraft batteries into devastating defenses. By late 1944, V-1 South were being destroyed at rates that made the weapon tactically ineffective. However, this success came with a cost. Thousands of proximity-fused shells landed on British soil, and intelligence services had to work overtime to ensure that none fell into German hands through espionage or captured duds. The British countryside was systematically swept for unexploded ordnance, with special attention given to any shells that might contain VT fuses. The Germans, for their part, never successfully reverse-engineered Allied proximity fuse technology, despite having opportunities to try. Several factors contributed to this failure. First, their electronics industry was being systematically destroyed by Allied bombing. The precision manufacturing required for proximity fuses demands stable, sophisticated facilities with skilled workers and specialized equipment. By 1943 and 1944, German industry was operating under constant attack, with critical factories being relocated to caves and salt mines. Second, German research efforts were fragmented. The multiplicity of proximity fuse programs, more than 30 different projects pursuing various technologies, meant that resources were spread thin and coordination was poor. Third, and perhaps most importantly, time simply ran out. Even if German engineers had captured an intact VT fuse and understood its principles perfectly, they couldn't have gone from reverse engineering to mass production to field deployment in the months remaining before Germany's surrender. This brings us back to the central mystery of how British engineers managed to reverse engineer magnetic mine technology so quickly at the war's start, and what lessons that experience taught them about protecting their own proximity fuse technology later. The key was that magnetic mines, while sophisticated, operated on well-understood physical principles. British scientists already knew that magnetic fields could trigger explosions. They had been working on their own magnetic mines since World War I. When they captured a German magnetic mine, they weren't starting from zero. They were examining a specific implementation of a concept they already understood. The reverse engineering effort was about understanding the details of the German design, not discovering entirely new physics. This meant they could work quickly and develop countermeasures rapidly. Proximity fuses represented something different, something more advanced. The miniaturization of radio components, the ruggedization necessary to survive gun launching, the signal processing required to distinguish genuine targets from false returns. All of these were cutting-edge technologies that pushed the boundaries of 1940s electronics. An enemy who captured a proximity fuse wouldn't just need to understand magnetic principles or basic radio theory. They would need to replicate advanced miniaturization techniques, develop rugged vacuum tubes, solve complex timing and safety mechanisms, and then mass-produce all of this with extreme reliability. This was a far higher barrier to entry than magnetic mines had been. The British experience with reverse engineering had taught them to make their own weapons as complex as possible, ensuring that even if the enemy captured examples, they couldn't easily replicate them. The post-war analysis of captured German and Japanese research facilities revealed just how close or far these nations had come to developing their own proximity fuses. The Japanese photoelectric proximity fuse, while ingenious, was limited by its daytime-only operation and sun angle sensitivity issues. German radio proximity fuse programs had made significant theoretical progress, but had never reached the point of producing combat-ready hardware. Both nations had brilliant scientists and engineers who understood the principles involved. What they lacked was the combination of industrial capacity, time, and resources needed to turn theory into mass-produced reliable weapons. This is perhaps the ultimate lesson of the reverse engineering story. Understanding how a weapon works is not the same as being able to build it, deploy it, and use it effectively. The weakness that the British engineers had identified in magnetic and proximity weapons, the vulnerability to reverse engineering and countermeasures, turned out to be less critical than feared because of the sheer complexity involved in exploiting it. Yes, magnetic mines could be countered through degaussing once the principle was understood. Yes, radio proximity fuses could theoretically be jammed or spoofed. But developing and implementing these countermeasures under wartime conditions, with bombed factories and limited resources, proved beyond the capacity of the Axis powers. The Allies won not just because they developed these weapons first, but because they had the industrial capacity to produce them by the millions and the time to refine them through multiple iterations. By war's end, the proximity fuse had evolved through several generations, each more sophisticated than the last, each harder to counter even if the enemy understood the basic principles. The legacy of this technological race extends far beyond World War II. Modern military technology still grapples with the same tension between deployment and security. Smart weapons, stealth technology, advanced electronic warfare systems. All of these represent capabilities that could be devastating if they fell into enemy hands and were successfully reverse engineered. The lessons learned from the proximity, fuse, and magnetic mine campaigns of World War II still inform how militaries think about technology security today. The fundamental question remains the same. How much security do you sacrifice for operational effectiveness, and how much effectiveness do you sacrifice for security? There's no perfect answer, only calculated risks and constant vigilance. And there you have it. The incredible story of how British engineers reverse-engineered German magnetic mines in the desperate early days of World War II, how that knowledge contributed to the development of the proximity fuse, and how the fear of enemy reverse engineering shaped the deployment and security of what became one of the war's most important weapons. This wasn't just a story about technology, it was about brilliant minds working under impossible pressure, about calculated risks that could have gone terribly wrong, and about how a weakness in one weapon system taught engineers how to protect the next generation of weapons. The proximity fuse went from requiring 2,500 shells per aircraft kill to just 250. It saved thousands of Allied lives. It helped defeat the kamikaze threat. It protected London from V1 South. And it did all of this while remaining secure enough that the enemy never successfully copied it, despite having every incentive to try. That's an engineering triumph that deserves to be remembered alongside the more famous achievements of World War II. If you found this story fascinating, I've got tons more historical deep dives coming your way. We're talking code breaking, secret weapons, technological races, and the brilliant people who shaped history from behind the scenes. Hit that subscribe button and turn on notifications so you don't miss the next video. Drop a comment below telling me what you think. Did the Allies make the right call, restricting proximity fuse use to overwater initially? What other World War II technologies would you like me to cover? The debate section is yours. And if you really want to support this channel and get early access to videos like this, plus bonus content and extended interviews, check out our Patreon in the description below. Every bit helps me keep diving deep into these stories and bringing you the kind of detailed, well-researched content you won't find anywhere else. Thanks for watching. And remember, the greatest victories in history often came from minds that could take the enemy's best weapon, understand it completely, and then build something even better. Until next time, keep learning, keep questioning, and keep exploring history.